We're going to be talking about the effects of air density on the aerosol transport capability in local exhaust ventilation systems. From now on, we're going to mention to them as LEVs. Basically, LEVs are the engineering control of choice for the exposure control of most chemical hazards in the work environment. There are some instances where we can use wet methods, but in the majority of processes where there is emission of chemical hazards, local exhaust ventilation is seen as the control of choice. To put us a little bit into perspective about what the study is about, air density depends on temperature. The higher the temperature, the lower the air density. Depends on elevation. The higher the elevation, the lower the air density. It depends on absolute humidity. The greater the humidity, the lower the air density. And also depends, for industrial ventilation purposes, on the duct static pressure. So the higher the static pressure, the higher the air density. Well, another important piece of information, when we talk about density in the study, we talk about density factor, and density factor would be the actual air density divided by the standard air density, which is 0.075 pounds mass per cubic foot. And another important concept is velocity pressure. For us to understand the difference between velocity and velocity pressure, let's say we're driving our vehicle on a highway, we put the window down and our hands outside the window. The pressure we feel on our hand is basically velocity pressure. It increases with the square velocity. As you can see here, velocity pressure depends on density. So the lower the density for the same velocity, the lower the velocity pressure. That is to say, if we're driving our car at 50 miles an hour at sea level, we're going to feel a certain pressure in our hand when we stick our hand outside the window. If we are in Colorado at the same speed, we're not going to feel the same pressure. We're going to feel less pressure because the air density in Colorado is lower than the air density at sea level. Well, the worldwide reference for the design and diagnostic of industrial ventilation systems is the American Conference of Governmental and Industrial Hygienists Industrial Ventilation Manual of Recommended Practice for Design. We are at the 30th edition, last published in 2019. The current recommended method for designing these systems is called the velocity pressure method. And it primarily, the two primary parameters for designing an industrial ventilation system for the extraction of contaminants in the workplace is the minimum transport velocity and the hood actual flow rate. We know for a fact that the current design method is quite effective for systems that operate close to standard environmental conditions. So what triggered our interest in this research study? Well, I have several colleagues that work in mines in the Andes in Peru that are about 4 miles high, and they are about 3/4 of a mile in the ground. So they are effectively 3¼ miles above sea level, and they have to extract contaminants from whatever process they're working on. There are several issues that were raised by industrial hygienists in those work environments, as well as from industrial hygienists that are working in very hot processes where the air is very hot and very humid. When you look at the pictures that are presented in this slide, you see on the left-hand side a duct that is almost completely filled with material. This is an industrial ventilation duct. It should not be filled with material. It should be perfectly clean. On the right-hand side, you see a duct almost 3/4 filled with metal powder. It was disassembled because part of the duct started to fall on top of the workers. So we have this problem, even though systems are being designed with the traditional method. So when particulates are collected in an LEV system, it is extremely important that they effectively move through the system. If they don't, we have reduced airflow through the system, which lowers the contaminant collection efficiency and negatively impact worker health. If they don't, increased weight of the ductwork with potential failure of the duct support hangers create a potential hazard for worker safety. And finally, if they don't, increased risk of fire and exposure by deflagration from particulates that can burn create a potential hazard for worker safety. Bottom line, if they don't work properly, if contaminants are not effectively conveyed through an industrial ventilation system, there's a lot of ways workers' health or safety can be affected. Duct settling has traditionally been assigned or attributed to improper initial design and maintenance, or to alteration that somebody did on the system once the system was already commissioned and implemented. But what about the effective density? We went back to publications from 1935 that were the origins of the industrial ventilation manual. None of these references, none of them, make reference to air density as an important design parameter. So we basically designed a study with two primary hypotheses. The first one, if we maintain velocity constant inside an LEV system and we operate it with different air densities, as the air density decreases, this air will have a lower ability to push contaminants through the ductwork, and there should be more settling inside the ductwork. That's one of the research hypotheses. And the second, but what if we maintain velocity pressure constant, which deals with the kinetic energy of the airstream inside a ventilation duct? What if we maintain velocity pressure constant inside the same system and we operate it with different air densities, just like the system on top? The amount of contaminant settling inside the ductwork should remain constant, irrespective of air density, if velocity pressure were to be a better design parameter than velocity. So based on these two assumptions, we design and commission a real local exhaust ventilation system that you see here on the left, on the right-hand side, to convey a control mass of powder material through 50 feet worth of ductwork into a high efficiency filter, which is this box here on the right-hand side. And here we see, courtesy of Mr. William Howard, a three-dimensional 3D drawing of this system so we can better appreciate. I'm standing here right in front of the hood. Basically, the air comes in through this hood, material is fed through this feeder that you can see here on the right-hand side with a control pace, so a control feeding rate, and the air moves through the system through all these loops until it gets to the drop box or the filter box, where basically the air is filtered and then goes through the fan. What we're measuring here is the amount of material in different conditions that is settling inside the ductwork. Our experiment was conceived to test two design methodologies, as I mentioned: constant velocity pressure. All methodologies were tested at 5 different elevations. That's where we got most part of our density. Emerald Isle in North Carolina at 14 feet above sea level, Asheville, North Carolina at 2,046 feet above sea level, Denver, Colorado at about 5,190 feet above sea level, Evergreen, Colorado at 7,980 feet above sea level, and Arapahoe Basin ski area at 10,910 feet above sea level. Each design methodology was evaluated 3 times in each elevation for a total of 6 runs in each elevation. The response variable was the conveying efficiency that was measured based on how much material is collected by the filter divided by the total amount of material that was fed in each experimental run. That lasted 30 minutes. The design parameters values were the velocity was maintained at approximately 979 feet a minute. That was the constant velocity. And VP, velocity pressure, was maintained at approximately 0.06 inches of water gauge. In standard conditions, both design parameters coincide. In other words, when density factor is equal to 1, velocity is equal to 979 feet a minute, correspond to a velocity pressure of 0.06 inches water gauge. The design parameters were controlled through continuous hood static pressure monitoring, the hood static pressure. Here you see a picture of the hood and the static pressure probe, measuring the static pressure of air getting into the hood within a thousandth of an inch of water gauge resolution. Here you see we had redundant systems and very high quality digital manometers to monitor hood static pressure. And just a little bit, you can see here the material being fed into the system while the system is working. As the results, as you can see here in this scatter plot, as the elevation went up, our density factor, total density factor, went down. The results, as you can see here, all in red is constant velocity. As you see, the conveying efficiency lowers down and decreases quite significantly with density, which coincides and correlates to elevation, while velocity pressure maintains almost constant throughout the entire density spectrum. Here's a interval plot, 95% confidence interval plot for velocity on the left, for velocity pressure on the right, showing that our hypothesis, the velocity pressure hypothesis, is much more appropriate for the design. So in terms of constant velocity, we recommend against constant velocity as the design parameter to keep contaminants from settling into ductwork. We recommend velocity or constant velocity pressure as the design parameter for keeping contaminants from settling into the ductwork. And basically, the way to the R2P, the research to practice, how do we implement this into the design is basically with a design density adjusted minimum duct velocity, which would be the minimum duct velocity recommended by the manual divided by the square root of the actual density factor where the system will be implemented. It's important that we acknowledge everybody that participated in the study. The study was not done by myself alone. We have Mr. Dylan James, who's a bachelor's undergraduate study student at North Carolina at Chapel Hill. Mr. Rob Dayringer, CIH. Mr. Edgar Perez Matias, who is a doctoral student at UPR Medical Science Campus, and Mr. Jonathan Hale, chair of the Industrial Ventilation Committee. All of us participated actively. Here you see some of the pictures. Some of the study began while nobody was vaccinated still, and everybody had to work hands-on for the system to operate and for us to be able to collect the data. Important to acknowledge the intellectual contributions of Mr. Jonathan Hale, who is chair of the Industrial Ventilation Committee, Mr. Robert Dayringer, CIH, member of the Industrial Ventilation Committee at ACGIH, and Mr. Edgar Perez Matias, who I, like I mentioned, is a doctoral student of our program, and is the PI of the redesigned pilot project that will be presented next year. For operational and data collection support, Mr. Dylan James, Mr. Jonathan Hale, Bob Dayringer, Mr. Edgar Perez, and Mr. Mark Pavel, who helped us with identifying the dimension of the material that we used, the size distribution of the material that we used. And for all the 3D drawings, Mr. William Howard on behalf of Ventilation and Fan Consulting Services International. Now, very importantly, I need to acknowledge New York and New Jersey ERC Pilot Project Program for sponsoring 42% of this project, where 24% was also sponsored by the Graduate School of Public Health at the University of Puerto Rico, Medical Science Campus, Department of Environmental Health. 9% of the study, Mr. Jonathan Hale on behalf of Air Systems Corporation. 7%, Mr. David Kennedy, who provided all the duct work for us on behalf of US Duct. 6%, Mr. Robert Dayringer, CIH. 5% indirect costs from our account. 4% personal funds from the PI of the study. 1%, Mr. Patrick Current, CIH, and Mrs. Mary Carol Current. Another 1%, Mr. Tim Finnegan on behalf of Arapahoe Basin Ski Area, and 1%, Mr. Mark Pavel on behalf of Blunder Products. Sorry, I went back. And finally, we dedicate this study to somebody who was very, very important to us and made and all the positive impact the study may have on workers' health all around the world, to Mr. Patrick Current, CIH. Mr. Current, with 3 weeks of life left on him, decided to spend 3 of his days, of his last 21 days, shuffling material with us in Emerald Isle, North Carolina. So we dedicate the study to this industrial hygienist whose dedication to the profession is so high that he dedicated, almost over 10% of his last days for this study. Thank you.